Okay, morning everyone. Let's get started. So first of all, I would like to emphasize again about homework 1. Please, homework 2. Please start doing it right now. I know that for the boosting and bagging framework sounds straightforward to many of you, but it does need some time to run to get the results. If you take a look at the homework requirement, actually we want you to run your bagging and boosting algorithm for many times to check the consistency to what we have discussed in class. For example, we want you to check the variance, the bias, the variance decomposition, right? So you have to run the random forest and bagging decision trees for many runs. It takes quite a lot of time, right? So yeah, if you haven't started, I would suggest you guys to start right now to give you enough time to run to get the results. The implementation itself, I believe, is not hard for everyone, but you need some time. You need some time to run and collect the results. That's very important. Yeah, and someone asked that, okay, like, what if I do not successfully implement decision tree in homework 1, right? And can I provide source code for decision tree? No, unfortunately, we'll never release source code because we don't want those code to spread and to affect students for the subsequent, either next year or next semester. If you feel like your decision tree implementation is still problematic, please take your time because we got 3 weeks to do the homework too, right? So if you just try your best to implement that. So I think for the boosting algorithm, where you need to just to implement decision stump, you only grow your tree for 1 level. That is, I believe that's much more straightforward, right? You shouldn't have any problem to implement that. Right? For decision tree, you can continue work on that. Plus, the time you have time and efforts you have made for your homework 1, that should be enough. But again, if you feel you need some help, and you please stop by the office hour. Our office hour is still quite empty, right? And bring your code and chat with our TA, or even chat with me, and let me try to help you, right? So don't don't just say, okay, I cannot do that, I cannot do that, without making any efforts, right? So just try your best to do that, right? If you try every possibilities and still feel difficult, and then let me know. Okay, so let us continue with the linear models. So in the last lecture, we talked about the formal definition of linear models. It's basically, we're assuming the output has a linear relationship with the input features, right? So assume that the output function can be written as a linear combination of the input features plus a bias parameter. That's a linear model. It's very simple. If you're doing linear classification, then we use this linear function serves as a score, right? You just check out the sign of the score. If the score is not no less than 0, then you predict positive label, right? Otherwise, you predict negative label. That's the definition of linear models, right? Then we'll talk about the expressivity of linear models. We use the Boolean function as an example. So, for example, we talk about conjunctions and disjunction functions, right? They can be perfectly represented by linear models, right? So just do this quick review. Like, for example, if I got a Boolean function, conjunction function, which is conjunction of 3 Boolean variables, right? So it can be represented as y equals to 1 if and only if their summation is no less than 3, right? Because y is 1 if and only if all the 3 Boolean variables are 1s. Otherwise, it won't be 1. And then from this condition, we can derive a linear classifier, right? So that means we just need to check if the summation from x1 to x3 subtracted by 3 is no less than 0 or not, right? it is no less than 0, then it is positive. Otherwise, it will be negative. Right? 1, 0. Right? So accordingly, you can build up a linear classifier where the weight vector will be 1, 1, 1. The bus parameter was -3. Right? And we can make some modification over this conjunction. For example, we can put some negation in front of one variable, say x3, and converting this into a equivalent linear classifier is also straightforward, right? Because negation of x3 essentially is 1 minus x3, right? So you're using the same condition that will give you y equals to 1 if and only if x1 plus x2 plus 1 minus x3, okay? No less than 0, no less than 3, and then you just do some simple arrangement. You got your linear classifier, which is x1 plus x2 minus x3, no less than 2, right? You got a weight vector, you got a bus parameter. So another example I want to showcase is the so-called M of n functions. Right? That sounds a little bit more challenging. Right? So M of n functions are a particular type of Boolean function. We're assuming you got n input variables. Of course, they are Boolean variables. And our rule is that y is true if and only if at least m of the n input variables are true. Right? So all the other variables are ignored, no matter they are true or false, it doesn't matter. So as long as m variables out of the n total variables are true, then your output, your function value is true. Right? For example, suppose there's 3 Boolean variables, x1, x2, and 3, right? And I can define 2 or 3 rules. That is, at least 2 of these 3 Boolean variables are true. Then my function value is true. Right? So now question, how can we convert this M of n rule-based Boolean function into an equivalent linear classifier? Right? How can we do that? Yes, it's relatively straightforward, right? It just require that, okay, x1 plus x2 plus x3 is no less than 2. And that's it, right? And then what is the weight vector? 1, 1, 1, right? And bus parameter will be -2, right? Okay, any questions so far? Oh, this is not, we're not talking about any benefits. We're just talking about the expressivity, how flexible the linear classifiers are. I mean, there is no practical benefit of using linear classifier to, represent those Boolean functions. We just want to discuss, okay, what type of family of Boolean functions can be well represented by linear classifiers to give us a concrete sense how flexible they are. Any other question? Okay, so now we come to the question. It seems that for this simple conjunction, disjunction, and M of n functions, they're all well represented by linear classifiers, right? So now comes to our question, right? Can linear classifiers represent any Boolean function? Why? From our previous discussion, we know that any Boolean function can be represented by decision trees, right? We know decision tree is really flexible and expressive, although it seems straightforward, right? But for linear classifiers, actually, it is less expressive than decision trees. In other words, not all Boolean functions can be represented by linear classifiers. So here I will give you one well-known example. That is, if your Boolean function is contains parity, then it is not linearly separable. Right? So here is the figure to give you an intuition. Right? So I got 2 I got positive examples, negative examples. And here are the how those examples are distributed. You can see that along this line, this is where our positive examples are distributed. And along this line, these are negative examples, how they're distributed. So the positive examples are have like two clusters, right? And negative examples have two clusters, and they're just located in this symmetric way. And you can try that. You can try to draw any type of lines. You won't be able to separate all the positive examples from all the negative examples. Right? That's a well-known and famous counterexample for linear classifiers. So if we want to talk about what does this specific Boolean function, what is this specific Boolean function name, right? It's called XOR. XOR. So everyone knows as XOR, right? If two variables are they're XOR, meaning that it must be different, right? Either x1, x2, one is 1 and 1 is 0. It will be 1, otherwise it will be false, right? So, and this is called parity. So if that means if this Boolean function x is a vector of the Boolean variables, parity means that f of x is 1 if the number of ones in x is even. In such case, we can show that you won't be able to find a linear classifier to well separate positive and negative examples, right? So this is actually the famous example given by a book written by Marvin Minsky. He's a pioneer of artificial intelligence, and because later we'll talk about when we talk about perceptron, you see that you can view it as a very, very infant level of neural network. But in that way, people are just trying to online learn a linear classifier, and then the perceptron is really hot for quite a few years until Marvin Minsky wrote a book and telling that, okay, linear classifiers are really limited. For example, the XOR function, you won't be able to find a well-separated hyperplane. So, and there are also many other non-trivial Boolean functions which cannot be linearly classified. So I have to say that, I mean, from historical view, after the book written by Marvin Minsky, people realized that linear classifiers are really limited in expressivity. Then the research and passion of linear classifiers kind of dropped down to, to some low point, right? But later people found a way to sidestep this issue. How can we do that? Here is a concrete example to illustrate the idea of to overcome this problem of linear classifiers. So for simplicity, we just look at one-dimensional feature vectors. So meaning that every point is just represented by a number, right? So we got positive examples, we got negative examples, stay on this axis, right? Single axis. Are these examples are linearly classified? No, right? You cannot find a line which can separate these 4 positive examples from the remaining 8 negative examples, right? Won't be able to do that. But we still want to use linear classifiers. How can we do that? There's a very, very smart idea. That is, the idea is as follows, right? We'll come back to this idea again. That is, now that in the original feature space, those examples are not linearly separable, why not I change the feature representation? I make some transformation about those features, right? For example, I just add one more feature, but this additional feature is computed based upon the original feature. So we know that the original feature is just x, right? Just a single number. Now I add one more feature for each example. This feature just take the value x squared. Right? Now I represent each example by a two-dimensional vector, right? Not just number. Then let's see in this two-dimensional space how our training examples, are distributed. So if we just do it, you can see their positions are rearranged, right? Now can you tell me, are those positive and negative examples linearly separable? Yes, right? You can just draw a line, right? So you can see that after some smart feature transformation, we're likely to separate those examples with just a linear classifier, right? And you can see that this feature transformation does not need any additional information, right? It's just based upon the existing features or the original features. Nothing needs to be there's no additional information source needed, right? So that's the smart. Why is this idea smart, right? As long as you can construct a new feature vector based upon the existing or the original feature vector, and you map them or you lift the feature representation in a higher dimensional space, then it is much more likely that you can find a linear classifier which well separates the positive and negative examples. Okay. So later we will talk about how we're gonna convert linear classifiers into nonlinear classifiers. This feature mapping technique is a very, very important trick, right? And when it combined with a kernel trick, and it reduces the so-called support vector machines. Right? If you just parameterize those feature transformation, then this is called neural network. Okay, any questions so far regarding the intuition about this? Okay. So now I will leave it as an exercise for you. Like we know from our previous discussion, the X4 Boolean function won't be linearly separable, right? So can you now think about a smart feature mapping or transformation such that when you lift the dimension of the feature vector in the new space, you can linearly separate out the positive and negative examples represented by XOR function. Right? This actually has been included in our homework. Think about that. Okay. In practice, because the data is often not perfect, right? It can be corrupted with noises, all kinds of stuff. So you won't expect that your data is always linearly separable, right? So in many cases, you can say the data is almost linearly separable, meaning that if you want to find find a line which exactly separate every positive and negative examples, that won't be possible. You have to draw some curve. However, you can find some line which separate most positive and negative examples. Right? This is in practice very highly acceptable, right? You don't like, for example, I know that okay, in this case, these positive examples, negative examples are not correctly separated by this line, but all the remaining examples are correctly separated. Then that's doable. Right? That's practically useful. Right? You wouldn't say, okay, because of these two outliers, I'm gonna give up my robust, trustable linear classifier. Right? So this is called almost linear separable. So then in practice, I mean, if you want to train a linear classifier to fit such a almost linear separable data, right, we need to like set some trade-off, right? Like how much noise would we allow for, right? In other words, how many outliers do we allow our linear classifiers to misclassify, right? That's something we need to tune in practice, and also it depends on the applications. Later we'll talk about support vector machines. We'll see that in the formulation of support vector machine learning objective, there is literally a hyperparameter and allow you to flexibly tune this threshold. But this is just some intuition to give you some sense, so that next time when we talk about that, it can make you recall something we discussed. Any question? Oh, yeah, but if you separate by x-axis, you can see that this one is still misclassified, right? Yeah. I mean, that depends on how you're gonna allow this noise level, right? If you believe, okay, I choose just parallel line to the x1 axis, right? I might get even better separability than this one, right? But there are some other metric you need to consider. For example, the regularity, the margin stuff. Those are related to the generalizability. So which we haven't discussed so far. So you see that this is actually a trade-off. It's not like, okay, the better I fit the training data, the better your generalization performance, right? Because of noises, right? I don't want overfitting, right? But at the same time, I don't want my training errors to be too large. Yeah. So that's why I said, okay, this is a trade-off. Right. Another question? That's a very good observation. Yeah. Okay. So now we finished the introduction, the formulation of linear classifiers. So overall, it is an expressive hypothesis class because many functions are linear, and also a good starting guess for hypothesis space. Meaning that if you want to choose a machine learning model for your application, you can start with linear classifiers. It is always give you some reasonable starting performance, and then you can check and see like if this is sufficient. If it's not sufficient, well, you need to turn to more complex models, right? However, we need to be aware that some functions are not linear, like XOR function, non-trivial Boolean functions, right? But as later we'll discuss, by using smart feature transformation, we have ways of making them linear in a higher dimensional feature space. So the last thing about the definition of linear classifier is, why is the bias term needed? Why should we introduce this bias term? We know that the bias term means that like this, you got two features, x1, x2, right? Each feature has their own weight, W1, W2, and we do want to add an additional bias parameter. So the problem is that why do we need this bias parameter? What if we get rid of it? Yeah, exactly, right? If you get rid of B, then you can imagine that your hyperplane, your classification boundary always go to 0, right? You won't move them. You won't move them off the origin, right? This actually restricts the flexibility, right? This might be fine for data set like this, right? But if you have same data set like this, right? Definitely you don't want your linear classifier to be always passing through the 0. Right? You want it to have some flexibility to move toward this direction, right? To well separate them. So that's just we want to give this concrete example to explain why we do need this bias parameter, because we want to maintain a certain kind of flexibility. Okay, so now we're going to talk about our first linear model learning algorithm. It's called least mean square regression. Right? So you haven't taken any statistical class before. you might have already learned this. Okay? Please bear with me. Our class need to be general to students from all kinds of background. Right? So so far, we're going to talk about definition of linear classifiers, what kind of functions do linear classifier express, and so on, right? And before we proceed to learning algorithm for linear classifiers, we would like to first introduce linear regression. The reason is that the linear regression model is learned, the learning method is quite the same. I mean, there are not too much variance of ways of learning a linear regression model. That's why we're going to discuss that first. But for linear classifiers, there are a variety of algorithms. And those different algorithms reflect different ideas. So for linear regression, we'll introduce the so-called least square method. We'll give some concrete examples to show how we're going to formulate the problem as linear regression problem. Then we'll talk about how we're going to formulate the learning objective for linear regression. Right? Then we'll talk about how do we optimize this objective, which we're going to introduce two very important framework, and also the most important framework in general machine learning paradigm. It's called gradient descent and stochastic gradient descent. Okay, so let us start with a concrete problem. Like, suppose we want to build up a machine learning model to predict the mileage of a car from its weight and age. Okay. For example, you might have this car whose weight is 31.5 times 100 pounds, and you have driven for 6 years, right? And I look at the odometer, right? Odometer, and it says, okay, you have a span like 21. Okay, this could be 21,000 or 210K, right? On miles, right? You got another piece of records like this weight and this from this year's, you got 25,000 miles and so on, right? And suppose you have collected a list of records. Right? Can we learn a model to predict the mileage given a new car, a different car, right? With its weight value and driving age, right? X1, X2, right? Of course, there can be a variety of machine learning models for choice, right? But here, if we use linear regression model, we're going to model the mileage simply as a linear combination of your weight and age plus some bias parameter W0, right? So this is our model. Right? So the mileage is modeled as some bias parameter W0 plus W1 times X1 plus W2 times X2. X1, X2 are the two attributes of your car. Then the learning task is to use the training data to find the best possible values of the weights W, right? So here the bolded W means a vector that includes W0, W1, and W2. So we call them as the parameters of the model collectively, a vector. Okay. Then once we learned W vector, right? Given the values of X1, X2 for new car, we can use the learned W vector to predict the mileage for the new car. Does it make sense? Any questions so far regarding this problem definition? Okay, so now we're going to give a general formulation of linear regression model. So suppose our training inputs are vectors of dimension D. Right? And the outputs will be a real number. That's why we call it regression, right? If the output is a discrete number, like 1, 2, 3, 4, those kind of things, this is called classification, right? If the output is just two discrete variables, 1 or 0 or -1, 1, called binary classification. Right? When we talk about regression, the output must be real numbers, right? Okay. And for simplicity, we will assume that x1 is always 1. What does it mean? It means that we're gonna put the bias parameter here, right? So we use simplified notation where we'll only use one single vector W to represent all the model parameters, right? And remember, it must include the bias parameter, right? And it is equivalent to, okay, I'm gonna injecting a constant feature 1 into a feature vector. So now I represent my augmented feature vector by 1, x2, x3 to xd. Right? So they are denoted by this bolded vector x. Right? And then I'm going to approximate the output as a function of the input vector x, which is w1, remember this is bias parameter, plus w2 x2, plus plus wd xd, which is w transpose x. Okay. And also we suppose we have collected a training set of m examples, which are pairs of input vector and output numbers. Then our goal is to learn this with vector W in this d-dimensional space. Okay, any question regarding the definition here? Okay, yeah, perfect. So now let us take a look at what we will learn, right? Suppose we only have one-dimensional features, right? One-dimensional feature vectors. So then your learned classifier or your learned predictor will just be a line, right? Your linear regression model will be represented as y equals to w1 plus w2 x2, right? Which is just a line. In this two-dimensional space, you can imagine that this blue points, blue dots are the training examples. And if our features, input features are two-dimensional, right? And then all those examples are located in a three-dimensional space, right? And then our predictor, our linear regressor, will be a plane, right? Like this one, right? And you can see that this plane will cross the training points, which are red dots here. And of course, if you further increase the dimension of input feature vectors, well, your predictor will be a hyperplane. Okay. So now, the question is, how do we find the best weight vector according to the training data set? To answer this question, right, we need to first define what do we mean by best, right? How do we know which weight vector is the best one for a training set? This is like when we discuss decision tree, right? We want to say, okay, our greedy strategy, okay, I want to maximize the purity improvement after doing every split, right? But the problem is, how do we define purity, right? You have a variety of ways to define purity, right? Based on entropy, based on majority error, based on, say, Gini index, right? And here, we also have a lot of ways of doing that. And different ways of defining the so-called best weight vector leads to different learning algorithm. And here, we're going to use the so-called least mean square formulation. So what does least mean square mean, right? First, right, given any weight vector, right, we want to evaluate, okay, how well it is, right? Then we're gonna pick up any input pair, right? Input and output pair, say xi, yi, right? And I can use my current weight vector to make a prediction, right? And my prediction will be simply W transpose xi, right? Now I'm gonna measure the difference between the ground truth output and my prediction. So I take the absolute value of the difference because the sign doesn't make any sense. It is meaningless to me, right? So we know that the larger the difference, the worse the prediction, right? So I'm gonna use this difference as the cost of the mistake, right? Meaning that the larger the difference from your prediction to the ground truth, right? The larger the cost you will need to make when you use a current fit vector for prediction, right? So in this way, we define a cost. But if we just take absolute value of difference as my cost function, and then we define some training objective, you see that it will very unfriendly for the training, because you always want to use some gradient-based approach. For training, if you take a gradient over absolute value of something, right, it's always awkward, right? So in practice, we usually take the square of the cost. And then we can define this cost function for a particular weight vector on a particular training data set as follows. Namely, we take the square of the difference between my prediction and the ground truth for every example, right? And I sum over all the training examples. And I use this summation as the cost measurement of using my weight vector to make prediction, right? And obviously, the smaller this cost, the better my model fits the training data set, right? And this function is also called loss function. So when you read the literature, right, in machine learning, like cost function, loss function, you can view them exchangeable. Interchangeable. Yeah, that's a good question. So we put this constant in front of just for convenience, because when you take the gradient, you got a fraction, this power will move in front of it, right? And 2.5 just cancel. That's it. Actually, if you erase it, it doesn't change any result. Any other question? If you optimize this cost function, meaning that I want to minimize this cost function to find the best weight vector, right? If you follow this way, this is called least mean square regression. Why is it called least mean square regression? You can see that from the name, right? Literally, you want to minimize the summation of the squares of your cost, right? Summation of square cost over the training set. This is called least mean square. And the strategy of learning is to find W with least cost on the training data set. This is how we design the goal of our learning. Essentially is to convert it into a optimization problem, right? This optimization problem wants to seek a weight vector W, which minimizes the cost on the training set. So any question regarding our formulation of the training or learning objective? Everyone's comfortable? Okay, great. So now let's see how we solve this optimization problem, right? So the learning is conducted by minimizing the sum of squared error. So here cost can also be called error, right? Because it's just the square difference between the ground truth and your prediction. So it can also call error, right? And to solve this optimization problem, right, you got different strategies, right? And here we're going to talk about a very popular and very dominant approach. It's called gradient descent. Right? So what is gradient descent? I'm going to use the gradient information about this learning objective to guide or to conduct the update of the weight vector until we make this weight vector to arrive at the minimum the objective function, right? This is called gradient descent, right? So let us look at the general framework. So we're trying to minimize this objective function. We know that is the summation, half of the summation over the squared errors on the training set, right? So if you write down the shape of this objective function, suppose this W, we're just saying staying in the one-dimensional input space, it'll be like this, right? So we're gonna start with some initial guess of W. We denote it by W0, right? You can use, you can say initialize W as 0 vector, or initialize as some random vector. Then we're gonna do the following iterations. In each iteration, we're gonna compute the gradient of our objective function J at the current weight vector, which we denote by WT. Then we update WT to get WT plus 1 by taking a step in the opposite direction of the gradient. This is called gradient descent. I believe most of you have heard that before, right? So what does this optimization go, right? We can use this example, right? So suppose this is my W0, right? I just random pick up position in this axis, right? As my initialization. Now, following this framework, right? I calculate the gradient of our objective function at W0, right? So now, what does this gradient look like? Is the gradient positive or negative? Positive, right? Why? Because you can take a look at the slope, right? The slope is positive, meaning that the gradient must be positive, right? So then we're gonna update our W by moving from the current position toward the opposite direction to the gradient. Right? And what does it mean? Yeah, it's pretty the same, right? But which direction we're gonna move? The opposite direction, right? If we move along the right-hand side, right? Move to the right, actually you follow the gradient direction, right? But now we want to move along with the opposite direction of the gradient, meaning that we're gonna move to the left. Right? And now I get W1. And again, I'm gonna calculate my gradient of the objective function at W1. Again, according to the slope, we know that the gradient is positive. Okay. That means I need to follow the opposite direction to move my weight vector. Now actually it's the weight number, right? Because it's just one dimensional, right? So now I get my W2. Right? Yeah, just keep doing this, just keep doing this. You can see that we're literally moving toward the minimum of the objective function, right? And in theory, we're going to converge to the minimum of the objective function, right? This is called gradient descent, right? And the intuition is that the gradient is the direction of increase in the objective function. So if you want to decrease the function value, right? You want to get the minimum, right? We should go in the opposite direction. So here is the general framework of doing gradient descent for least mean square. So we initialize W0, right, as our initial weight vector, right? Then we just go through many iterations, right? Until the maximum number of iterations down, or until some threshold or tolerance level is down, right? In each iteration, we compute the gradient of the objective function at the current weight vector, right? We denote by this nabla J, WT, right? Then we update W with the following rule. WT plus 1, meaning that the updated W, right, is obtained by subtracting the current W, WT, by some constant R times the gradient of objective at WT. This R is called learning rate. Okay. You see that in practice, actually very, very important. Okay. So now, for now, let us assume, okay, R is a small positive constant. Right? We'll get to this later. Right? And then we finish the update of W, right? Then we'll move to the next iteration. Again, we compute the gradient of the objective function at the current W and get the gradient and the update with the same rule. We just do it again and again until a certain number of iterations are done or some other stopping criterion is satisfied, right? Okay, so the remaining question would be, given any W, right? How do we compute the gradient of our objective function? Then we need to do some review of our basic calculus. Right? Again, this is our objective function. It's a summation of square of the errors. Right? And then our gradient vector for W will have the following form. Right? This is just literally how we define the gradient vector. Right? So each element in this gradient vector is a partial derivative of our objective function with respect to one weight element. Right? So remember our weight W, the weight vector W contains D elements, so it can be represented as D W1, W2 to WD. Right? Then that means if we want to compute the gradient vector, we need to figure out a way to compute each partial derivative. So let us look at if we can find a unified formula to do that. Suppose I pick up any element, say WJ, in your weight vector, right? I want to look at what is partial derivative of the objective J with respect to partial derivative of WJ, right? So that means I'm going to take the partial derivative of this sum of square function. So we know that we can just move the partial derivative inside each summand, right? So that means, okay, I'm going to take the partial derivative of this squared error. Right? Applying the chain rule, right? You're going to first do 2 times yi subtracted by w transpose xi, right? And then you take the partial derivative over this difference, right? So now, what's this? I will ask, what's this? What is the partial derivative of yi subtracted by our prediction with respect to wj? Any? xi actually is a vector. As a vector consists of a series of features, right? But now we want to take the derivative with respect to the weight element wj only, meaning that only the jth element in the weight vector. What's it? Yes, right. So that actually is determined by the form, right? So we know that this w transpose xi can be written as w1 xi1. xi1 means that okay, the first feature is xi, right? Subtracted by w2 xi2, right? xi2, the second feature in xi, right? So you see that every feature in xi is associated with a different weight element, right? So that means wj is only associated with the jth feature in xi, right? Which we denote by xij. So if you take the derivative, right, all the other terms are constant to wj, right? You only need to care about the term that involves wj, which will be wj xij. Does it make sense? Right? Then you give the derivative will be just minus xij. Because it's just linear combination, right? Linear combination of each weight element with each feature, right? And y is constant to wj, so this derivative was simply minus xij.
And now we have observed that 2.5 here are canceled, right? So, and if we move this minus sign, like minus in front of the summation, we got our final results. So you can see that the partial derivative of the objective with respect to each weight element is simply as a summation. Each summand is the error, right? The prediction error times the associated feature, associated J feature for every input vector, right? And just add them together. And you add, then you this way, you compute one element of the gradient vector, right? You just go over every element, you compute the full gradient. So that's it. Right? So any questions so far? And like if you feel uncomfortable with this, I highly suggest you guys to follow the slides after class and derive this. You got a question? Yes. Yeah, we'll come to that point later. Yeah, we're going to discuss later. Mm-hmm. Mm-hmm. Oh, that's a good question, but this is more practical. In theory, no matter how much skill difference you are, in theory, they are going to converge. But in practice, what you say is that, okay, if you do not reskill them into like same range, right, or similar range, your converge will be very, very slow. Right. So in practice, people will first do the normalization of each feature. And then you conduct gradient descent or stochastic gradient descent to make it converge faster. Right. But here, we're gonna not talk about that level of details. Right. But your question actually is very useful for practice. Okay. Any other question? I mean, just about to understanding this derivation. Okay, great. So now, oh, by the way, yeah, your question is about, okay, if I just derive the global minimum of this least mean square objective, yeah, we can do that. But later we'll see that when the number of training examples is large, even you can derive the analytical form, the computation will be very, very expensive. That's why, yeah, invert the matrix, right? That's why in practice, people would rather prefer to use, optimization algorithms. Okay, so now that we got, we figure out how we're going to compute the gradient, right? We can fulfill more details about our gradient descent algorithm framework, right? So we initialize our weight vector, we denote by W0, right? And we go through many iterations. In each iteration, I compute the gradient of our objective at the current weight vector, right? The calculation is as follows, right? Once we have finished the computation, I use my gradient vector to update the weight vector, right? And we need to carefully choose the learning rate R. Cannot be too large. If it's too large, it won't guarantee the convergence. And we just keep doing these iterations until, say, the total error is below threshold. You can take a look at, you can just evaluate this objective function. See, the objective function is less than like 10 to minus 3 or 10 to minus 4. You can stop, right? It's up to you. The choice of the threshold is up to you. Right? And in theory, the algorithm is guaranteed to converge to the minimum if R is small enough. Right? And for this particular objective function, the minimum actually is the global minimum. meaning that when it converges a global minimum. The reason is that the objective J is a convex function. Okay. I guess we have tried in our homework 0, right? We try to prove or show if a function is convex or not, right? So again, I will leave it as an exercise to try to show that this is a convex function. Okay. So any question regarding the gradient descent framework for least mean square? Everyone feels comfortable and feels straightforward, right? And yeah, I literally want to confirm with everyone is because in our implementation, you're gonna follow this framework, this arrows in table to implement, right? Just to make sure everyone feels comfortable. Multiple learning rate. I'm sorry, I didn't catch up. You mean multiple what? Multiple learning rate or multiple gradient? Oh, okay. For this one, it only contains one minimum. So if it's a convex function, right? If it is convex function, you either have only one minimum or have infinite many minimum. Why? Let me draw a figure for you. So convex function usually looks like this, right? When we say, okay, it has infinite many of minimum points, it usually means it's just a line. Now, in that case, like whichever position is fine, right? Or it could be something like this, right? But then the minimum will be just negative infinite. Right? And for this case, this is a quadratic function. And you can show that it doesn't. It only contains one global minimum. Right? Of course, like later when we talk about more complicated classifiers, the objective function could be non-convex. In that case, your shape of the curve could be like this, right? And then we usually only consider just arriving at one local minimum will be fine. Any other question? Okay. So the next thing we want to discuss is that what kind of problem of the classical gradient descent approach? From the formula of gradient calculation, right? This is what we just derived, right? We know that to calculate one gradient element, we'll have to go through all the training examples, right? Just to compute one gradient, right? You have to go through all the training examples. Naturally, we want to ask, right? What if our training set is huge? For example, you got 1 million training examples, right? In that case, even you just compute one update, you have to go over all the training examples, all the 1 million training examples. So imagine it's very, very, very costly, right? And nowadays, like training set, you got 1 million training examples, you can only view as maybe it's just a small to middle size of data set. It's not common to use like billions of training examples, right? In that case, if you just use standard gradient descent, imagine you go through all the training examples, you can only conduct one update. This is very, very costly. A natural question will be, can we have a more efficient way to update our model parameters, namely the weight vector W? If we look at the calculation of the gradient, right, which are circled here, so you can see that actually our gradient is accumulated over all the training examples, right? That means, okay, I have to compute this error feature product all over every training example. And then I get one gradient. I do the update, right? The bold idea will be, okay, why should I wait until I go over all the IM training examples, right? IM could be 1 million, IM could be 1 billion. That's too costly. Why not I just calculate one such kind of product? I use it to update my weight vector. That means, okay, I'm not gonna doing this summation, right? I just pick up one example, X and YI, I calculate my prediction error, multiply the corresponding feature, right? I use that to approximate my gradient and update my weights. Yeah, it's a bias, right? That's a problem, right? But the intuition is here, right? I mean, very naive or very bold intuition is that, okay, to reduce the cost, right? I'm not talking about, okay, whether it's correct or not, right? Whether it's correct or whether it's valid, right? That if you want to reduce the cost, that means I want to increase the frequency to update my model parameters. How can I do that? Okay, when I come to see one example, I just calculate this product, right? And I just use it to update my model. If doing this, imagine that, okay, when I literally go through all the training examples, say I'm equals to 1 million, right? When I finish the path through the whole training set, I have already updated my model for 1 million times, right? If you use a standard gradient descent, you just update once. Obviously, if this simple, ugly trick looks like it's much more efficient for model update. You got a question? Okay. So to summarize, this idea is that, okay, why not make an early updates to the weight vector as soon as we encounter errors instead of waiting for the full pass over the training set, right? So someone may ask, right, is doing this valid, right? Although it looks like, okay, I can do this updating much more frequently. Look at each update is erroneous, right? Is incorrect. Will there be any guarantee about that, right? And the answer is yes. We can do that and have a strong guarantee of that. If we're doing this method is called a stochastic gradient descent. And actually the most dominant technique right now in machine learning area. Right? People always use stochastic gradient descent. People rarely use the full gradient descent. So here's the general framework of doing stochastic gradient descent. We just go through every training example in the training set, X and Y. Right? Then we pretend that the entire training set is just represented by this single example. Now I just use this example to calculate gradient, update model, and use this example to calculate gradient. This gradient is called stochastic gradient because it's not true gradient. Right? It's just the stochastic estimate of the gradient. Right? And later we'll talk about the theoretical justification. So this stochastic gradient can be viewed as the unbiased stochastic estimate of the true gradient. Right? As long as your gradient estimate is unbiased, you can show that with probability 1, or almost surely, your learning will converge to some local minimum of your objective function. So that means stochastic gradient descent also guarantees convergence. But today we're not going to talk about these details. We're going to in the subsequent lectures, at some point, we're going to go back and to contrast these two frameworks. One is called batch gradient descent or gradient descent. The other is called stochastic gradient descent. We're going to talk about their pros and cons, and we're going to talk about in which scenarios we should prefer which one. Like, which one should we prefer, right? So contrast with the batch gradient descent, which makes one update to the weight vector for every pass over the data, right? So stochastic gradient descent make an immediate update once we process a single example. So now let us take a look at the framework of all the algorithm table of doing stochastic gradient descent. Right? First, we're going to initialize our weight vector W. Right? You can initialize as full zero or actually, and then we do many iterations until the error below some threshold, right? And inside each iteration, we're going to pass through every training example, say xi, yi. Then we just calculate the error of predicting this example and multiply it with the corresponding feature, okay? And then I update my weight accordingly, use the gradient descent rule. Right? But of course, this gradient is no longer a true gradient. It's a stochastic gradient. But you're going to still move your weight of weight vector toward the opposite direction of your stochastic gradient. Right? And because the stochastic gradient has a negative sign, right? You're going to subtract your current weight by your stochastic gradient. So 2 negative ends up with positive. That's our final rule. Okay. So this update rule is also called the Virchow-Hopf rule in the neural network literature, right? So like the neural network people first come out this simple, intuitive, fast trick, and then people start to look at the theoretical guarantees and properties. And online or stochastic algorithms are often preferred when the training set is very large, right? And interestingly, I will discuss about that in detail later. In many cases, applying stochastic gradient descent can get close to the optimal much faster than batch for you. That's an interesting observation. Okay, so any question regarding the stochastic gradient descent framework? It's not about smaller data set, because when the data set is smaller, stochastic gradient descent has no advantage over the gradient descent. So usually when the data set is huge, stochastic gradient descent can often observe to converge faster than using full gradient descent. The reason, there are some kind of theoretical analysis, but basically you can view like when objective function is very large, and also in many literature, objective function is not a convex function, nice shaped convex function, right? Using stochastic gradient descent is like a drunk driver, like you randomly try all kinds of direction. It make you have a larger chance to find a local minimum. But for the true gradient descent, you're gonna always align your direction towards the exactly the function, the descent of the function, descent direction of the function. It's sometimes it is even less efficient than you use gradient stochastic gradient descent, say, to jump in this way. So that's why people find stochastic gradient descent is much more preferred in a large data set, right? And later when we talk about the convergence rate analysis, you will see some mathematical form to reflect that. Okay, so again, our homework, you're going to use stochastic gradient descent to implement your least mean square, right? Just follow this framework. So I want to make sure like everyone feels comfortable with that, right? Although it seems straightforward. Okay. So now let us talk about the learning rate issue. So in both the standard gradient descent and stochastic gradient descent, we talk about, okay, we need to multiply our gradient or stochastic gradient with a small constant value R, right? We call it the learning rate, right? In general case, right, if you're using stochastic gradient descent, right, your learning rate R must gradually decrease. And at the limit, it should decrease to 0 so that we can guarantee the convergence of the stochastic gradient descent. Right? In some other literature, the learning rate is called step size. Right? Although in our class, we're going to give some very simple schedule of the learning rate, right, which guarantees it is monotonically decreasing, and also it will decrease to 0 in the limit. Right? In the modern machine learning algorithm, there are a variety of learning rate schedule approach, which can automatically adjust the step size or learning rate. And you actually don't need to care about that. Right? It's already being used as a black box. Like first, for example, the most popular stochastic gradient descent algorithms is called ADAM, ADAM. Okay? Actually uses the learning rate for different weight. So you got a whole weight vector, right? Right now, we're assuming that, okay, the whole weight vector, they're going to share the same learning rate, right? But in the modern machine learning research, right, or practice, people use different rate for different weight elements. And they have their ways to update them automatically, like momentum-based approach, right? But this is but we're not going to that details. Right? Just give you a sense, right? And although for the convex objective function, right, we know that from whichever place you start, you're going to convert to the same global minimum. But choosing a better starting point can have impact about convergence, right? For example, since this is your convex objective function, if you're starting from here, of course, you're going to converge faster than you start from here, right? And in practice, like if you use neural network or other learning algorithm, when the objective function is non-convex, might have many local minimum. Of course, the initial position or the starting position matters much. So in general, the gradient descent and its stochastic version are very simple algorithms, right? According to the framework, right? Yet, almost all the algorithm we will learn in this class can be traced back to the gradient descent algorithm. The only difference is that, okay, we're going to use different loss functions, right? Even including the perceptron linear classifier, which we're going to discuss in the next step, right? Later we'll see that is essentially another stochastic gradient descent learning for some objective function. So that's why the gradient descent, the stochastic gradient descent, is so important. Right? We're gonna go through it from time to time when we talk about different algorithms. Okay, so now we have finished our discussion about linear regression. So here are the summary. Right? The goal of linear regression is that we want to predict a real valued output using a feature representation of the input. Right? So remember, regression always to predict continuous values or real values. Right? If you want to predict discrete labels, it's called classification. And for linear regression, as the name suggested, right, the output is assumed to be a linear function of the inputs. Okay? And how do we learn the model parameters? In linear regression, we want to minimize a cost function over the training set. Right? The least mean square, that means our cost function is defined as the summation of the square error of using your model to predict every training sample, right? And then you can use gradient descent or stochastic gradient descent to optimize or minimize this cost function to find the best weight vector. Okay, so the last thing about the least mean square regression comes to the question you raised before, right? Actually, we can show that for least mean square regression, we can directly derive the optimal weight vector. And how can we do that? This again will leverage what we have reviewed in homework 0, right? If you represent our data in terms of matrices, right? So if you got your X matrix contains all the feature vectors, right? So which is D by M. Like you just stack all the input vectors together, right? And you got a Y vector, which contains all the training outputs. Right? Then your objective function can be written in this way. Okay. So X transpose W actually is the prediction of your model over every training example. And subtracted by Y is your error, right? Now you do the dot product, that means you just take the square of each error, right? And sum them together, you got your sum of the square errors, right? And then if you want to minimize this objective function with respect to W, what we can do is that we can take the gradient directly over this objective in the form of matrix and vector, right? And we will solve the gradient being 0, you can directly get the optimal fit vector in this form. So it'll be X transpose inverse XY, right? And I will leave it as an exercise for you guys to check this, right? And again, we want to answer the question why we not directly use this guy, right? The reason is that if your X is large, you take the inverse of this guy is very costly. Right? That's why in practice, we're not gonna use this one, right? But we can use that on small data set to check whether implementation is correct. This is also what we ask you to do in your homework. Okay, let's stop here today and see you on Thursday.